Hey guys, second part of chapter 8, that means lesson 11 for us. We're going to finish the critical path analysis and we will look at the last 3 points from this chapter. We will calculate the total float of an activity, and then we will use the Cascade Charts, sometimes called Gantt charts, and then construct the scheduling diagrams. First, just little review from the last lesson. You should be able to recall and to understand what is the early event time, late event time, critical activities, and critical path. So try to pause the video, write it, or think clearly what it is, and then we can compare our thoughts. So when you look at or when you think about the early event time, it's the earliest time each activity can start while it allows the preceding activities to be completed. The late event time is the latest time each activity can or must start if we do not want to delay the project, so without extending the time that is needed for the whole project. Then critical activities are the activities that satisfies two conditions. One condition is that the vertices on each side of the critical activity or of the arc that represent the activity must have early and late time the same on each side. That means, for example, it could be 4-4 on left side and 7-7 on the right side. That's one condition. The second condition is that the difference between these two numbers on the right side and left side, on the right vertex and the left vertex, must be the same as the duration of the activity, as the time the activity takes. And then finally, the critical path is the path that consists of critical activities from the starting to the sync node, and it's the longest path contained in the network. So, if this is clear, because this will be needed, you need to be aware of these concepts, we can move to the float of an activity, because the activities that are not critical, they have some flexibility when they can happen. Because if we start them a little later, it's still not going to affect the total time from the for the project. The float is found when you subtract the length of the activity and the early start time from the late finish time. That means late time minus the length of activity minus the early time will give you the float. As I said before, it's the time by which you can delay the activity without putting the whole project into danger of not be completed on time. So it basically describes how much flexibility the non-critical activities have. But let's just look at an example. So we are given the activity network here, and we need to find the float for the non-critical activities. The yellow one, I'm using the same example from before, so the yellow one are critical. And as you can see, the float for the critical activities must be equal to 0. 4 minus 4 minus 0 is equal to 0. Or as for case of C, 14 minus 10 minus 4 is equal to 0. And this is true for every single critical activity. But let's look at the non-critical ones. So let's start with the B activity. If you're looking for the float, then it's the late finish time, that is 8, minus the length activity is 6, minus the 0, what's the early start? So in this case, it should be 2. 8 minus 6 minus 0 is 2. The next activity, let's take the one that is not critical, is D. So 11 minus 5 minus 4, so the float is 2. That means you can delay 2 hours or 2 days, depends on which unit is used, this activity without putting the whole project into danger of not being completed on time. The next one would be activity E, 11 minus 3 minus 6, what is 2? So try to do the same for the rest of the activities. Take the pen into your hand or somewhere to write it and then complete it, this one. So F. The next one should be G. And last one for now should be H. So complete that one and then you can compare it. So F should have float of 2, G float of 2, and H float of 3. And then the last one complete. There will be 4 more, I guess. J. And then K. L. And N. And then you can compare if you got the same one. 2, 2, 3, and 2. So this is the float, how to find it. And let's try to do the guided practice with this concept. So in here I have a part of activity network with the activity times measured in hours. P is a critical activity, that's important to know, and that's why it's important to understand what the critical activity means. And Q has a total float of 3 hours. The questions are, we need to find out what the values A, B, X, and Y are. So let's start with this one first. A case, because P is critical activity, I know that the early time and late time at each end, in each vertex, at the end of the activity, I mean the arc or the edge that represents the activity must be the same. So from here, you can just write directly A is equals to 10, and then B is equals to 19. And because it's a critical activity, then you know that the duration of the activity must be the same as the difference between the numbers on each side of the activity. So 19 minus 10, what is X must be then 9, obviously. And then the last one is we need to figure it out also what's the Y value. But I know that Q has a float of 3. So if I have float of 3, I know that float for Q is 3 hours. And I know that it would be calculated as 15 minus Y minus 10. What is your A value? And that's equals to 3. So then from there, you know that this is 5, this is Y is equals to 2. So A, B, X, and Y are finished. B case is asking you to find out the minimum value for the C. So if you look at I have now Y equals to 2. So I know that 10 plus 2 is equals to C. 10 from here and 2 from here. This is your 2 and this is your 10. This is coming from forward scan or forward pass. When you're looking for the early time, because C represents the early time. So 10 plus 2 is equals to C. What is C is 12. This is the minimum value because of the Q having the float of 3, obviously that can be moved to 13 or 14 or 15, but the minimum value is 12. And then the C case is asking us to find out the maximum possible value of the total float for R. So we know that float for the activity is found when I'm going to subtract from B, what is my 19 now, I will take 4, the duration of the activity, and I will take C, what is the early time on the other end of the activity. So in this case, because I know the values already from before, so this is 19 minus 4 minus 12, what is then 3? So then the float, maximum possible float for the activity R is 3 hours as well. So the next topic is Cascade Charts or Gantt charts. They are called Cascade because they have the shape of the cascade once you finish them, and they are a good graphical way or graphical representation how you can see the start and finish times for all activities on the single diagram. The good thing to remember is that once you find the critical activities, they always must be put in the single line at the top of the diagram, as you can see. So in this case, A, C, F, and H are the critical activities. And then the other activities that are non-critical, you will put them with their early time and late time, and you will also show, this part is showing their flexibility, their float. Okay, so that means how much flexibility they can have. That's this shaded part represents, or this dashed line represents. So for example, you can read that the D activity must start from 3 and finish at 9, but there is a flexibility of 4 hours that you can move it a little bit. E activity must start at 3 hours and finish at 13, but also there is a 5 hours of flexibility. What is also good to point out that the scale of these graphs show the elapsed time. That means the time that has already passed, which means, for example, the first hour is shown between 0 and 1. Between 6 and 7 is the 7th hour of the project, or 7th day of the project. Okay? Between 13 and 14 is the 14th day or 14th hour of the project. So let's look at some example. If we're going to take the network from example 1 that we have seen when we were looking for the floats, we are asked to draw a cascade chart on the grid below. So what we need to do is to identify the critical activities that will represent the critical path in one single line. Okay, so we have the A, C, I, and M, where the critical activities. So C starts at 4, finish at 14. I starts at 14 and finish at 21. And M starts at 21, finish at 26. This also shows you the critical time that the project must be completed by. So the next step is to draw each non-critical activity on its own line. You can either skip one line on your graph, or you can just connect them directly. So for example, B is the first non-critical activity. So it started at 0 and finished at 6, but there is 2 hours of the float, because 8 minus 6 minus 0 is 2. So you can shade last 2 hours of the project, or last 2 little squares that represents the hours or days, the unit of time. So the next one is D. So D starts at 4 and finish at 11, but again 2 last squares represents the float. Then next one is E. E starts at 6 and finishing at 11, but when you look at the float is 2, so again shade the last 2. Sometimes I just do from 6 to 9 and then I add the float. It doesn't matter, it depends on your preference. So the next one is F. When you look at the F, that is starting at 4, finishing at 21, and there is a float of 2, so last 2 squares. Next one is G. G is 9 up to 13, but the float is 2. And now try to pause the video, finish it. I think I have 4 more activities, and then we can compare. So age was 6 up to 17 and the float was 3. Next one is J, is 11 up to 21 and the float is 2. Next one is K, 11 up to 22, float is 2. L is 14 up to 22, float is 3. And then the last one is N, 20 up to 26, float is 2. So let's look at the guided practice. We are given the network, we need to draw a cascade chart or Gantt chart, and the time is in hours. So we need to first identify the activities that are critical. So in this case, it should be A, then it should be C, 9 minus 5 is 4, then next one is E, and I have F, and then I have H. You can notice G is not critical activity because 16 minus 9 is 7, not 3, so this is not critical one. So first thing, what I'm going to do, I'm going to put the activities that are critical, so 0 up to 4, 0 up to 4, that would be my A activity. Then 4 up to 9 is C. Then I have next 3 is E activity. Next one is F is 2. And last one is H, also 2. So this also gives me the critical path. The next activity that is non-critical, I'll start with B. B starts at 4, so starts here, and it takes 3, so 1, 2, 3, and then I can shade the float. Float is 12 minus 3 is 9, and minus 4 is 5. So I have 1, 2, 3, 4, and 5. This is the float of the B activity. Or you can say, you can do it the same way as we have done it in the example 3 in the animation. So start at 4, finish at 12, and then find out the float and shade the float. Okay, both is okay. So B is finished, then I have D. D starts at 7. D starts at 7. It takes 2 hours or 2, well, whatever, yeah, hours. D. And then the float for D is 14, minus 2 is 12, and minus 7 is also 5. So 1, 2, 3, 4, 5. So this is my D. And then the last one that I still didn't do is a G. G starts at 9. Takes 3 hours. And the float is 16 minus 3 is 13 minus 9 is 4. 1, 2, 3, 4. So this is the cascade chart or Gantt chart to represent the whole project. Now, the next part is quite easy because it just talks about how do you interpret the cascade chart or Gantt chart. They are useful because from here you just look at one chart and you can see which activities must be happening at the given time and which activities may be happening at the given time. So how it works, let's look at the example 5. We are given the chart and we need to decide how many workers do we minimally need on day 6 and on day 19. So what does this mean is we assume that every task is assigned for one worker. And then the minimum number of workers needed on any time you can identify by drawing a vertical line and seeing how many tasks must be happening. Okay, so let's look at it. Day 6. Day 6 is happening here. Between 5 and 6 is day 6, right? You can see that definitely C activity must be happening because it's critical activity. B activity also must be happening on day 6 because either way, even when you use the flexibility for the B activity, it still will, this vertical line, the blue one, will pass through the activity. That means it definitely must be happening. So B activity still is the activity that must be done on that day. Now D, if you move the D and instead of 4 you start at 6, it may be happening but doesn't have to, because you can escape the blue line, right? So D doesn't have to be done on day 6. And then F, for the same reason, doesn't have to be done. And that's about it. So for this day, you definitely need 2 workers for the 2 tasks, and that's task C and task B. So when we're going to look at the day 19, we're going to draw the line between 18 and 19. So from here, you can see that definitely I, because it's a critical activity, must be done on day 19. The same way, when you look at the activity F, this also must be done because either way you're going to move within the float for the activity F, then it still can escape the blue line. So I and F must be happening. The same is true for J and for K. And let's look at L as well. Okay, either way you're going to move it this way or that way, it still cannot escape that line. So for this one, we need 5 workers, and that's the task I, F, J, K, and L. Now, why I talk about it is because the minimum number of workers that you need to complete the project on time is equal to the maximum number of workers needed on any day or any hour or any time, any point in time. So in this case, you can see the 5 was the maximum number of workers needed. That means it's the minimum number of workers that you need for the project. So let's look at this part. I think it's pretty easy. When you look at it, we need to determine 3 activities that must be happening at midday on day 10. So it's here between 9 and 10, yeah? You can pause the video, try to answer these 2 questions, and then we will compare. So if you try to answer, you can see what I can do is to draw the line between 9 and 10. That's this one. And then you can see the activities that must be happening are definitely C and then D, because even if I move it 3 units to the right, it still will have 1 unit passing through the blue line. So D as well. And then I also have E, because E can escape. When you look at F, and if I move it 2 units to the right, then it's not passing, I mean the blue line is not passing through the activity. That means it doesn't have to be happening. And that is actually the answer for your B case, because it asks you to determine one additional activity that may be happening at midday on day 10, but doesn't have to be, and that's the F activity. Because if I move it, it doesn't have to, but it may happen if I do not move it. So the same chart, please pause the video, try to do day 8, 21, and 22, and then we will compare it. So when you look at the midday of day 8 is this line, this part. So this is the day 8, this is for the A case. And when you look at, okay, I'm going to write it here, day 8 must be happening. So if you have done it, then definitely A must be happening, and definitely E must be happening. D doesn't have to, because I can postpone it. So B case, I have day 21 must be happening. So 21 is between 20 and 21, that's this one. So the ones that must be happening is definitely G. And then it's H. And I can escape because I can move 3 units to the right. And then the last one, day 22, midday 22, that's the last line here. And I want to find out the activities that may be happening. So J must happen, F may happen if I move it all the way there to the right, and then H may happen, and I must happen there, yeah, because either way you can escape the last blue line. So on day 22, the activities that may be happening is F and H. The last part of this lesson is a little bit tricky. It's about the scheduling diagrams. Why is it tricky? Because there is not always only one correct answer. You can find out the answer that will be different from the one given in the book, for example, but usually it's written that that's not the only one correct answer. But the good thing about it is you can always double check that your answer that you're presenting is the correct one by the checking the diagrams or the activity network. So the scheduling is a process when you assign the workers to activities. You might remember what I said before, that you always assume that each activity is completed by one worker, by single worker. You always use the first available worker that is in the group. And if there is a choice of tasks for a worker, you will assign the one which has the lowest, latest finish time. So if I have 2 tasks that I can assign to one worker, I'm going to choose the one that have the latest event time, the lowest. This scheduling diagram, when you finish it, when you complete it, it shows you which workers should be assigned to which activity. Okay, so basically it's like the schedule in the school. The last thing what we will talk about is to find the lower bound for the number of workers that you need to complete the project within its critical time that is given from the Cascade chart or from the critical path analysis that you found before. You can find out how long time you need to complete the project, and then you can find out the lower bound or the minimum number of workers needed to complete this project within the given time. The ratio that is given here, that means when you add all of the activity times together and you divide it by the critical time of the project, that gives you the estimation of the number or the minimum number of workers that you need, but you need to round it up, obviously. So let's look at example 8. We need to schedule the activity so that the process is completed in the shortest time. use the number of workers you found in example 5. So this is for example 5, that's what we have done there. And we found out that we need 5 workers because on day 19 it was the maximum number of workers needed at any given time during the project is the minimum number of workers that you need for the whole project. So I need 5 workers. The first thing what you will do is to assign all critical activities to worker number 1. This is always the same, okay? So if you have a critical activities, you give it to 1 worker because there doesn't have to be any waiting time. I mean, in reality, obviously, it doesn't mean that this person is going to work 26 hours, but it's the one position for, 1 worker is needed for that. 1 person is needed for that. So next one is worker number 2. So I start with the B activity. You can see it starts at 0 and finish at 6. There is a float, but I'm following the early event time and late event time. When this is finished, when B activity is finished, the D activity or E activity could start. D can start if you move the D here, if you move it to the right side, okay? And that's why I said you can see there is not only one possible answer, okay? So in this case, I assign D because I can move it, okay? Then the next activity, when D is finished at 11, I can see with the G in here, I can also move G, I can postpone it, and I can start at 11. And next one would be J, because that also has a flexibility time of 2. So if I move it, I finish at 21. And that would be it. No, actually, I can actually move the N, because if I move N 1 unit, then it starts at 21 instead of 20. And then the worker 2 can complete also this activity. So now I move to, I have B as well, this is finished. So I'm going to move to worker 3 and I'm looking at the ones that I didn't touch yet, the activities. That means E can start at its original time 6. And then the next activity I didn't do, well, I cannot do anything about F because even if I move it, even if I move 2 units to the right, it still cannot meet the time when the E will be finished. So I'm not looking at F at the moment, but I can definitely look at H, because if I move H 3 units to the right, that means it starts here, it's exactly where E finished. That means H can go, H can start when E finished. And then the next one, so H is finished at hour 17. So I'm looking at 17, which activity could start. And I can see that L can start if I move it all the way down to the right. And then the last worker, there is one more activity that has not been completed yet, and that's the F activity. But I can see that in case of, so F is done now also, but there is one more activity that is K, and I cannot move it anyway that the worker 4 could complete it, so I need another worker for that. And that's the worker number 5, which will complete the activity K. So this is the scheduling diagram, and I have 5 workers. Worker number 1 is responsible for all critical activities. Worker number 2 has the activities B, D, G, J, N, and then 3, 4, 5 has the rest of the activities. Obviously, you can switch K and F, for example. Yeah, that could be switched. So that's why I said there is not only one possible answer. So let's look at some guided practice in this section of creating the schedules. Example 9 shows the Gantt chart for a project. So this is the one that we talked about before as well. And we need to schedule the activities to be completed in the critical time, that means 25 days or 25 hours, by the minimum number of workers. So what I'm going to do, so this is the chart from before, the Gantt chart, the Cascade chart, and what I'm going to do is to do the worker by worker. So as we said before, the first worker is responsible for all critical activities. That means I'm going to assign him all critical activities. So A is 0 up to 8. 0 up to 8. This is A activity. Then C activity is 8 up to 16. This is C. Then I have G activity 16, 21. And then 21, 25 is J. So this would be my worker number 1. Now, next one, I'm going to do worker number 2 here. So this is done, and now I'm starting with the B activity. So B activity is between 0 and 6. 0 and 6. That would be the B activity. And then you can see from the Cascade chart that when B finish, D can start. That means this worker can take care of the D. D is between 6 and 13. So 6 up to 13 would be the D. And that is about it. Let me see, can I move the... Actually, I could move, because when you look at F, so D is finished, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So it starts here. If I move it all the way, that means F can be assigned to the same worker, because D finish at 13 and F can start at 13. So I have 13 all the way up to 23. 13 up to 23. This is your F activity. And then this worker is running out of time, then there is no other activity I could assign, because it's finished at 23. So I need to start with the next worker, worker number 3. And the activities I still didn't schedule is the E, what is good because it starts at 6 and finish at 17. So starts at 6 and finish all the way up to 17. So this is E. And then for this worker, when E finish at 17, H can start at 18. And so there will be 1 hour break for this guy. So 3 hours. It takes 3 hours to complete. Is the H. And you can also see that when I move the I activity 1, 2, 3, and then 1, 2, 3, so that starts here. So when H is finished, then I have 4 units reserved for the I activity. That means here. Sometimes what you can do is to shade this space here. This would be the place or the time when the worker 3 would not be active. So it's not required to be there. What is important is when you finish to check your final diagram to make sure that all dependency conditions are satisfied. If one activity has been delayed, this might affect the earliest possible start time for the other activities. So in example 10, we are asked to find out the lower bound for the number of workers from example 9. That's why I'm going to use the same chart from before, because we will need that information. You may recall that lower bound is the sum of all activities, and when you divide this sum by the critical time or critical time for the project. So in this case, when you look carefully, in this case it would be sum of the all activities. So I just start at A is 8 hours or 8 days, C activity is 8 up to 16, so 8. Next one is G. G is 5 hours. Next one is J is 4. And you will do this for every single activity. And then you will go all the way up to I, and I is 4. And then you divide it by the critical time for the project. In this case, it's 25 days or 25 hours. So when you add all of these, then you will get 67 divided by 25, what is 2.68. You always round this number up, so the lower bound for this project is 3 people or 3 workers. Bound is 3 workers. Now, what that means is, this means that it's impossible to complete the project in the critical time, in 25 days or 25 hours, using fewer than 3 workers. But it doesn't take into the account how the activities might overlap. That means it doesn't guarantee that 3 workers is sufficient, that it will be enough to complete. But minimally, you need 3, okay? If you will go under 3, then definitely you will not make the critical time. And as the node recommends you, in case that will happen, that you will have less workers available than is the lower bound, it's still okay to go ahead with the project, but obviously you must count with the fact that you will not be able to finish it in the critical time, and the project will be delayed and the time will be extended. And in this case, if this happens, that you have less workers than the lower bound, then it's better to schedule directly from the activity network, so you ensure that dependency conditions are met and followed. So let's look at a similar example. Example 11 shows you the activity network. The completion time, you can see it's 31. That's a critical time for the project, should be completed. And we need to use a scheduling diagram to find the new completion time for the project, given that only 2 workers are available. Okay, so I'm going to copy the activity network below here, and I only have 2 workers. So worker 1, and then I have worker 2. So what I can do is start with A activity. I will assign it to worker. First one, that means 8 hours or 8 days, I'm not sure. Days, yes. So 8 days, worker 1. But obviously, B cannot, you should not wait until the A is finished to start with the B, because then the delay would be really huge. But you have a second worker available, so he will start with the B. B has taken 6 days. So B activity. Then once A is finished, you can start with C. So starts at 8 and takes 9 days. That means it goes to 17. That would be the C. Okay, so A is finished, B is finished, C is finished or scheduled. And then you can see that for the, let me see, in here, look, at the D cannot start right after B, because D can only start when A is finished, right? So if you want to assign it to worker 2, then you can, but you will have 2 hours of empty space. And in the meantime, the same worker can start working on E activity. So I will rather give him E, so he starts at 6 and takes 5 hours, so it will go all 5 days. I mean, it will go all the way to 11. That means it's E. So this way, there is no empty space for the workers to wait. So the next activity that I can choose for worker 1 is either D or F. But because C finished at 17 and F starts there, so I would just give him F, that is 4 units up to 21. And I would keep the D activity for the other worker. When E is finished, that is at 11 days. And then I can definitely start the D. I can assign it for this worker because D has some float and it doesn't have to start at 8, it can start later, so it takes 7, so up to 18. That's D. So F and D is finished. The next available one, the activity that is next available is H and G and I as well. So I need to make sure which one can start. So after F is finished, I can give him H because H doesn't depend on F. H doesn't depend on F, and it doesn't depend on I. That means I can give him 8 units that goes all the way up to 29. That would be H. This would be finished. And J and I can assign to the second worker. So J takes 5 hours, that will go up to 23. 1, 2, 3, 4, 5. This is G. And then I is also 5 units. 1, 2, 3, 4, 5. This is finished. Now I know J depends on I, H, and G. I, H, and G must be finished between I, H, and G. I, H, and G. Okay, so all of them must be finished, so J can go here. This is 5 units. 1, 2, 3, 4, 5. This is J. And then K depends on E, what would be finished, and nothing else, so that can go here. K is also 5 units. And this is the empty space, yeah? He doesn't do anything there. So from here, you can see that if I only have 2 workers available, what is less than the lower bound needed, then the project time will be extended from 31 to 34 days. So the minimum time that is needed, is 34 days. When only 2 workers are available. When only 2 workers. This last part is a little bit tricky, but as we said at the beginning, in spite of the fact that you might have more solutions available, you can always make sure your solution is correct. As far as your dependencies are met, the conditions of the dependencies are satisfied, then you don't have to worry. You just have to make sure that they really are met, and then your solution is correct. So this would be all for this chapter. Please look at these examples from the set E, F, G, and I. The first 3 sets are quite easy because they are focusing on practicing the easy concept, such as finding the float, or creating the Cascade chart, or interpreting the Cascade chart, which activities may be happening and must be happening. So I think they are very easy concepts and very quick to practice. The tricky part might be in set AI, where you will be asked to not only to create a Cascade chart, but also the schedule, and sometimes recreate the schedule if you do not have the enough workers available. If the number of workers that you have available is lower than the lower bound, than the minimum number of workers required for the project to be completed on time. The answers are at the end of the book, as always, and the templates with the detailed solutions you can find online. If you struggle or if you are not sure and you want to double check, then obviously you can always find me. Otherwise, I'll see you in the tutorial. Bye guys.